As good as altitude and azimuth are as coordinates, there is one major flaw for the astronomical community. Even if I know where a certain star appears in my sky, this position will not be the same for another astronomer in a different location or viewing on a different date and time. So today we're going to discuss a more universal coordinate system, right ascension and declination, alongside why some stars don't actually set as we watch this space.
3, 2, 1.
Stars.
For these coordinates, you can imagine them as an extension of the longitude and latitude on Earth. If we project these outwards, we can map the stars' positions on this, the celestial sphere. Before we get to the actual coordinates, it is important that we define a couple of key things. Extending out from the equator, we have the celestial equator. And if we project outwards from the poles, we get the north and south celestial poles. The celestial equator acts as our midpoint for declination, which is our celestial equivalent of latitude, and the Greenwich meridian, our reference point for right ascension, which is projection of longitude into the sky. But hang on, I hear you say. Hang on. Thanks for that. If these coordinates stay fixed as a projection over these points on Earth, then they're going to move. After all, the Earth is orbiting the Sun and rotating on its axis. This would be a massive flaw and would do very little to make this coordinate system any better than altitude and azimuth. Thankfully, astronomers figured this out so that we don't have to. We still use the longitude and latitude of Earth as a reference point from which to measure the positions of the stars, but where they are on a specific day at a specific time. That time and day is noon on the vernal equinox, otherwise known as the first point of Aries. At that point, the Sun is directly overhead the equator at midday, something that only happens twice a year, here at the start of spring, and 6 months later at the autumnal equinox. As an aside, the equinoxes are the only days of the year when both poles are illuminated at the same time. Other than this, because of the tilt of the Earth, they actually alternate between 6 months of daylight and 6 months of darkness. You can see this on this chart of hours of daylight measured against latitude and date throughout the year. I'll be honest, it doesn't have a huge amount to do with today's video, but I thought it looked really cool and it was worth sharing nonetheless. Back to the coordinates, basing the origin of the right ascension and declination on where the Sun is at this point in time is really helpful, as this is where the celestial equator overlaps with the ecliptic, which is the path that the Sun takes through the sky. Probably the easier of the coordinates to explain is the declination. As explained earlier, this acts as a projection of latitude into the night sky, with 0 degrees of declination being above the celestial equator, and a range of values from plus 90 degrees at the north celestial pole to minus 90 degrees at the south celestial pole. The right ascension is perhaps harder to get your head around, as it isn't broken down into degrees. Instead, if we think about how one day takes 24 hours, then we can split the east to west direction of stars into 24 hours too, to match the rotation of the Earth, starting with 0 hours in the direction of the first point of Aries. As stars appear to move east to west across our sky, our right ascension increases as we head further eastwards. This means that the higher a star's right ascension, the later it will culminate relative to other stars. For example, a star with a right ascension of 6 hours will culminate 2 hours later than one with a right ascension of 4 hours. Looking at this on our celestial sphere, we plot our right ascension starting at the first point of Aries, heading east for an increasing angle, measured in hours ranging from 0 to just under 24. Our declination is measured north or south of this celestial equator with a range of plus 90 degrees to minus 90 degrees. The benefits of this coordinate system are huge over using altitude and azimuth. With RA and dec, we have a set of coordinates that are consistent throughout the year and not varying with date, time, or position of the observer. If you think of the wider community of astronomers and astrophysicists, having this as a common frame of reference to work in is essential and means that you don't have to work out based on an observer's location where you'd have to look at what time to witness the same celestial bodies. But that does not mean that it's a perfect system. One potential issue we have is that it's a tricky one to explain and to visualise. Unlike altitude and azimuth, where you're just visualising stars featuring in a sky dome above you, here you have to understand the motion of the Earth in its rotation and orbit, how its position relates to the Sun, and then where stars are going to be relative to that whole system on a specific date at a specific time. Another potential issue is converting from RA and dec into altitude and azimuth. Thankfully, this is something that you can find online. So, for example, here's a converter provided by the University of Cambridge. All you have to do is provide the RA, dec, your location, date, time, and credit card details, and it will calculate the altitude and azimuth for you. Okay, not the credit card details, but you do need the rest. Alternatively, if you go on software like Stellarium, when you click on a star, it will provide you with both sets of coordinates, as we can see here. Now that we've explained right ascension and declination, let's talk through something linked to a star's declination and your location, which is, will it actually set below your horizon? Going back on Stellarium, if we remove the Earth's atmosphere so that we don't have to deal with daylight and centre our view on Polaris, the pole star, then as we advance time, we can see that stars near to it never actually set. Instead, they seem to just circulate around the celestial pole. Stars that do this are called circumpolar stars. They only exist within a certain angle of the celestial pole, which is actually dependent on your location on Earth. If you live at a lower latitude, then the celestial pole appears lower in your sky, meaning that a smaller angle of sky can contain circumpolar stars. But if you're at a higher latitude, this will give you a higher celestial pole and a larger region for stars to circulate it and still remain above your horizon. We can see this with long exposure photography too. The star trails of circumpolar stars do not set, whilst other stars dip below the horizon. A star will be circumpolar if it satisfies this inequality, that 90 degrees minus their declination is less than their latitude. This means that if you are in, say, for instance, Paris at a latitude of 49 degrees, then any star with a declination above 41 degrees would be circumpolar. And also, if you lived on the North Pole, every star that's currently visible in your sky is circumpolar. I would love to see a long exposure image from here, as the star trails could be fantastic. Unfortunately, that's all we've got time for today, which means we didn't quite get to cover why coordinates for RA and dec are actually shifting by around 1.4 degrees per century, or how this system still doesn't factor in the distance to stars, meaning that there are actually better systems for mapping out the positions of stars within the galaxy, or relative positions of galaxies within the universe. But what we will be looking at next week in our series finale on stars and constellations is why different stars are different colours and why you don't get green stars. From there, we'll talk about how you can use this knowledge to work out just how powerful a star is. Until then though, please do have a look back at one of our previous videos, perhaps even the prequel to this one, focusing on altitude and azimuth. Thank you for watching today's video. Feel free to give us a like if you've enjoyed it, subscribe to the channel if you haven't already, and until next time, please continue to watch this space. Thank you.